All right. It's 4:05, and this is COMP2804, discrete structures 2. So, yeah, the question in the chat is what's going to be done about assignment 4? And to be honest, I'm still undecided. I wish I knew more about what the strike was likely to do. Certainly by the end of the day, Monday, I'll know for sure, because if the strike's not over by the end of the day, Monday, then we'll just drop assignment 4. Anything before then, though, I don't know. I will have to, I might try and get it marked. So Monday, end of the day is sort of the guaranteed drop date. I don't want to say anything definitive before then. It'd be nice if they were all marked, but yeah, I don't know. Just going to roll with punches. Yeah. Right. Yeah. But I mean, you had lots of time to work on it, I would say. And you still have lots of time to work on it. I mean, nearly a week. I guess that's not, yeah, I mean, I could take that into consideration too, if the power is going to remain out for a long time, but if the assignment is dropped, whatever marks I don't have accounted for will just be moved to either the test part of your grade or the assignment part, whatever is higher. So, if you happen to if you blew the first 2 assignments, you won't be, I guess, stuck with those grades. So yeah, that's the idea. Yeah, I know you guys want something more definitive, but I simply don't have an answer right now. I don't want to drop it right now. Day's not over. I don't know. And they might meet this weekend, and I don't know. I would like to get it marked if I could, but yeah, by Monday, for sure. If nothing is resolved, we'll just drop it. And then assignment 3 might get dropped as well, depending on how much longer it goes on. So yeah, I don't know. I'm sorry I don't have a better answer. I've been thinking about it all day, but I still don't have anything really good, any really good plan other than kind of wait and see. And I wish I knew more as well, but yeah. So yeah, other questions before we start? Well, let's see, where are we? We're on the 6th, Easter tomorrow. So today we're going to be talking about not indicator random variables, but the probabilistic method. So it's not really extra to the course, although we don't cover it directly on the final, but it still uses indicator random variables, but it just uses them in a way that is not immediately obvious you can use them, right? So we're going to prove things, properties about graphs in this case, that have nothing to do with randomization by themselves, but we can use indicator random variables and randomization to reveal properties, essentially. So yeah, that's where we are today. Yeah, I guess no other updates. The exam will go ahead as scheduled. It's the 24th, I believe. Yeah. Okay, so I'm going to start. We're going to look at 2 problems. Both of them are graph problems, which is kind of nice because you get that nice visual element. You're not always just staring at Greek letters and numbers. Section B does not get this lecture, no. But again, this is still indicator random variables. They're just being used in a different way. Like I said, the probabilistic method will not be covered directly on the exam, but we are still having indicator random variables on the exam, which everybody has taken at least, I guess, 3 lectures at this point, or 2 at least. So yeah. Okay, so the probabilistic method, in this case, we're going to prove some things about graphs. We're going to solve problems using probability, where probability is not really part of the problem, right? There's a couple of ways to do this. In this case, we're going to say something about, well, the expected value of a random variable is really the average. And so the average can tell us some things as well. So we want to prove the following, given a graph G, which is a set of vertices and a set of edges, right? So the vertices in this case, we usually draw our graphs, or often we visually represent them. The vertices will be these green circles, and the edges are of course the connections between the green circles. So we want to partition the vertices of our graph into two sets, A and B, such that the entire vertex set is covered, and A and B have no vertices in common, right? So that's what we mean by partition, is that, I have a set of elements and I'm going to make two sets. There is no intersection, but every vertex is in one of the two sets. All right, so then, and then an edge UV is between these two partitions A and B if I have one vertex in A and one vertex in B, essentially. Right, so I can either have U in A and V in B, or I can have V in A and U in B. And in both of those cases, the edge UV would be considered to be between these two partitions. So our claim is for any graph G, there exists a partition of the edges between A and B such that, there exists a partition such that the number of edges between A and B is at least half of the edges. Okay, so what does that mean exactly? Well, in this case, I have 8 edges in this graph, and let's say I partition it into A, which is A and D, and B, which is B, C, and E. Then I look at the number of edges that go between those two sets. So we have AB here, we have AE here, we have DE here, and we have DC here. So there's 4 edges between those sets. So this is a partition where the number of edges between A and B is at least half of the total. Okay, so, and we only need one such partition. We just want to prove that there exists a partition, not that every partition is at least half, but we just want to show that there is at least one for any given graph where the number of edges between the two sets is half of them, or at least half. Okay, so that is the problem. Any questions on the problem we're solving? Okay. So yeah, there's nothing random about this. We can choose the partitions and choose the graph and try and solve the problem. So no randomness enters into this, but we're going to use randomization to solve it. So yeah, this is our claim. And we're going to start by randomly partitioning the vertices of our graph into the sets A and B. So we start with 2 empty sets, A and B, and then we will simply look at every vertex in our graph and flip a coin. And if it comes up heads, we're going to add that vertex to the set A. And if it comes up tails, we're going to add that vertex to the set B. Okay, so we're just going to randomly divide the graph into 2 sets. And once we are done the algorithm, we have partitioned all of the vertices, right? So if we look at each one and each one has to go in either A or B, then we get this effect here. We've partitioned them. There's no vertices in common, but every vertex is accounted for. Okay, so then we will define a random variable. Of course, X is the number of edges between A and B. And well, now we can figure out what's the expected value of X because we have some randomness here to work with. So yeah, we're going to use indicator random variables to count the edges that actually go between A and B. And we can base all of this on randomness. So our expected value of X is equal to, essentially for each edge, I'm going to declare an indicator random variable Xi, and this indicator random variable is equal to 1. if this edge is between A and B and 0 otherwise. Okay, so just a typical indicator random variable to indicate if this edge goes between the two partitions. And of course, our expected value of X. So X will be, the sum of all of these indicator random variables, and then the expected value of X will be the sum of the expected values. So now we want to know what is the expected value for any of these given edges that they will be between A and B. All right, so let's look at, well, how did we choose this edge? Or how did we choose the partition of the vertices that are involved in this edge? Well, we flipped a coin, right? So what are our possibilities? Well, we can say that we flipped a coin and we had U and V both landed in the set A, in which case this indicator random variable is equal to 0 with probability 1/4, right? So this is simply based on 2 coin flips. I did 1 coin flip for U, 1 coin flip for V. So these are fair coins and it's a uniform sample space. So because it's 2 coin flips, our sample space is 4. So it's probability 1/4. The other possible outcome is both of them go into B. So this is heads, heads. This is tails, tails. If both of them go into B, then Xi is equal to 0. And this also happens with probability 1/4. Or I can have heads, tails, in which case U is in the set A and V is in the set B. And then our indicator random variable is equal to 1, again with probability 1/4. And then finally, we can have tails, heads, in which case U is in B and V is in A. And again, our indicator random variable is equal to 1. Okay, so if we look at this event, that Xi is equal to 1, it's just the sum of the probabilities of the outcomes. So this would be equal, this would have a probability of 1/2 that this edge goes between the two sets. Okay, so the probability that my edge EI is between A and B is 1/2. And this is, of course, also equal to the probability that my indicator random variable is equal to 1, which is also equal to the expected value of that indicator random variable. So now I can, find my expected value of X by finding the expected value of the sum of these indicator random variables, which is the sum of all the expected values, which is I equals 1 to M of 1/2 or M over 2. And then the claim is that we're done at this point. So we wanted to show that there exists a partition between of the edges. There exists a partition such that the number of edges between A and B is at least M over 2. And we've shown that on average, it's M over 2. All right, so what does that mean? Well, that means that, let's just informally prove it. If on average there's half of the edges between the two sets, then there must be at least one partition of the edges such that there's at least half, right? I can't have an average of a half if every partition is less than that, right? So we can assume, we can prove by contradiction, assume it's not true. So we have an expected value of M over 2, but every single partition, the number of edges between A and B is less than M over 2, well then that can't possibly be the average, right? The average will be, it's at most the maximum number of edges in any partition. Hopefully that makes sense. Sort of informal, but yeah, so that's, any questions? Okay, so that's basically a simple version of the probabilistic method where we took something that wasn't too hard to prove. We just said on average that, more than half the edges would be between the two sets. All right, and then, yeah, slightly more formally, if you're interested, you can take a look at this, but you can define a second random variable, and you can prove all of this much more formally. Well, it's the same in theory, essentially. But yeah. Okay, so yeah, we have used probability to prove a property that has nothing to do with randomization or probability. And a very simple example. At this point, there's the next example in these slides are a problem that is taken from the first lecture we did, or maybe the second, but I think we're going to skip that one because because I want to do the other one essentially. This one is maybe harder to follow, but the other one has to do with graphs too. So this first example sort of leads into it. And again, I don't want to, graphs are nice because there's pictures, so you can kind of visually see what's going on, and you don't always have to exactly follow the math. You can just sort of get an idea of what's happening. So yeah, I think, and this is a rather famous result. It's called the crossing lemma, which is actually, it's famous because it's sort of a high level result, but the proof is kind of simple. Not simple per se, but it's simple enough for this class essentially, which is sort of surprising. So again, given a graph G, which is a set of vertices and a set of edges, and the edges are unordered pairs of vertices. So yeah, this was actually a question on the final exam last semester. So if I give you this definition of a graph, V is a set of vertices, and then the edge set E is a set of edges, which is each edge is an unordered pair of vertices. All right, so then what is the maximum number of edges we can have? Yeah, that's about the response I got. They said it was not a fair question, but if you just forget about the graphs and just use the definition, I have a set. How many subsets of size 2 are there? The set is size n. How many subsets of size 2? Right, so we just choose all possible pairs from this set, right? So if I chose all possible pairs, it is n choose 2. Okay, so this is, somebody get it? Yeah. Okay, so I'll explain it one more time, but this is, we're doing a probabilistic method, which uses indicator random variables to prove things, but the probabilistic method will not be on the final. Indicator random variables and random variables in general will be. So yes and no. We're covering material that will be on the final, but we're also covering material that's not on the final. It's not even that it's not on the final, it's just it's a higher level than you can generally ask with multiple choice. Okay, so if you see this question, the answer is n choose 2. Simply because of the way it's framed, right? V is a set of vertices, E is a set of edges, and each edge is an unordered pair of vertices. That's all subsets of size 2 taken from V. Okay, so if we have a graph below that you can see drawn there, then the vertex set V is A, B, C, D, E, and F. These are all of the vertices. And my edge set is, well, all of the pairs, right? So I have, A and B, and that's here. I have A and D, and that's here, and so on and so forth. Okay, and we've drawn it, which is, we often draw graphs. That's sort of a nice way to visually represent this information. And when we do it, the vertices are a point, or in this case, a circle, and the edges are line segments between the 2 points. And yeah, that's a pretty standard way to draw a graph. And there's a couple things. Well, because of the way we defined it, well, this is a set of edges, which means I can only have one edge between two vertices. I can't have two. And each edge is an unordered pair of vertices. Yeah, maybe this should be set of vertices, which means that I can't have self-loops. Okay, so this is what's known as a simple graph. I can have at most one edge between two vertices, and each edge must be between two distinct vertices. So now, given this in our drawing, we have EF and AD are two edges that cross. And what's more, there's no vertex at the intersection, right? So these are just edges. I've drawn it such that they cross, right? This is what's known as a combinatorial representation of a graph, which is pure math. But now I've drawn it, and now I have a visual representation, and I have a crossing. Okay. Well, I can actually take this same graph and draw it a different way, right? Combinatorially, this is exactly the same graph because it's the same set of vertices and the same set of edges. But now I've drawn it with no crossing edges. Okay, so that's sort of, it might seem trivial, but that's sort of important when it comes to graphs because, well, okay, so first of all, if I have a graph G and I can draw it without any crossings, then it's called planar, right? So that's a special graph. So this graph here is planar, even though I've drawn it with crossings, because I actually can still draw it without crossings. There are some graphs it's impossible to draw without crossings, as we'll see. And so why is this important? Well, when we do things with graphs like model networks, microchips especially, you know, roads, things like that, when we have crossings, that's a problem. On a microchip, now that means I have to increase the thickness of the microchip so that I can run one wire underneath the other or above. Same with roads, of course, right? You have to make an overpass. So crossings are expensive in terms of whatever, usually whatever we're modeling, a crossing is expensive. So planar graphs are important. So if I have a graph that can be drawn without crossings, that's important. All right, so if we draw a planar graph without crossings, right, this is called an embedding in some cases, then these graphs, in addition to our vertices and edges, they have another property called faces, right? So I've drawn my graph here, and this graph partitions what's called the plane, right, which is just a two-dimensional area. So partitions the plane into different areas, right? Basically based on, and I mean, it should be sort of easy to see that if I have a section of the plane, or in this case, the slide, that is completely surrounded by edges, that makes a face. Okay, so I have, in this case, I have 1, 2, 3, 4, 5 faces, but we also count the outer face, right? So I can think of the entire area outside of my graph as a face as well. And you can think of this drawn on a soccer ball, and then, you know, which side is the front? Well, they're all faces if it's drawn on a sphere. Okay, so we have a graph. We have vertices, edges, and faces. In this case, we have 10 vertices, we have 14 edges, and 6 faces. And it just so happens that a very smart person named Euler, who discovered a lot of things, also discovered this property. If I take the vertices and I subtract the edges and I add the faces on a planar graph that's connected, then that expression will be always equal to 2. Right, and we're going to prove it, but yeah, this is true for every connected planar graph. Well, planar in the sense that it's embedded. Okay, so yeah. All right, so the proof goes something like this. We're just going to do an informal proof just to prove, you know. So I'm going to take my current graph here and I'm going to remove every edge. I'm going to look at a cycle. So a cycle means I have an enclosed face. And I'm going to remove one of those edges from that cycle, right? So a cycle means I can travel around and back to the original vertex. So let's say I take that edge out of that cycle. And then I'm going to say, well, this is also a cycle. So I'm going to remove that edge. And then I can remove this edge. And then maybe this edge and this edge. And at some point, I'm going to run out of edges to remove. I'm going to run out of cycles. I'm only going to have, at this point, it'll be a tree, and I'll have exactly one face. So yeah, this is a spanning tree algorithm, a simple one. There's lots of them. But if I run this algorithm until I run out of cycles, then I will have a graph that could look like this. There's a bunch of different spanning trees for this graph, but this is one of them. So what do we know about trees? Right. A tree is a graph with no cycles. That's the definition. So, and one of the things that you can show that I'm not going to here, we have enough things to prove, but the number of edges in a tree is equal to the number of vertices minus 1. And you can, I mean, at a high level, you can say that, well, if I just have a path, that's a tree. And it's clear in that case. And then every time I add a branch, I add a vertex and an edge. So then this equality will always be maintained. Right? So that's a sort of a loose proof of this equation. Okay, so we have a spanning tree based on our graph, and we have one face, right? There's no cycle, so there's only one face. It goes all the way around the entire thing. And if we plug these values into Euler's formula, well, if my edges is equal to the number of vertices minus 1, and my faces is equal to 1, then I get v minus 1 plus 1, which is simply 1 plus 1, which is 2. All right, so Euler's formula holds for trees. Hopefully that seems sort of clear. Questions so far? Okay. Yeah, all of this graph stuff is not, I mean, this is, we're going to learn a lot about graphs today as background for this, just because it's a kind of a cool thing, the crossing lemma. So the probability all comes in later. You don't have to know this graph stuff for this exam. It might come in handy in 3804. All right. So our base case is we have a tree, and we know that Euler's formula holds for a tree. And in this particular case, well, we have 10 vertices. We have 9 edges because we always have one less edge than vertices in a tree. And we have one face. And if we do the math on Euler's formula, of course, we get 2, right? That's completely expected. Now we're just going to add edges back in. So every time we removed an edge, we lost a cycle, we lost a face. Now, every time we add an edge back in, we gain a face, right? So here I add one edge. The number of edges increases by 1, but so does the number of faces. So then I can add another edge here. Well, now I have a second face here. And in fact, any edge that I add is going to create a face, right? Because an edge is between 2 vertices. So once I start adding edges to a tree, even if they're not the original edges, I'm going to create a enclosed area, another face. So when I add all of the edges of my graph back in, every time I do it, I increase the number of edges by 1, but also the number of faces by 1. So that means I'm subtracting one more edge and I'm adding one more face. So they're always going to sum up to 2. Okay, so that is sort of the, a bit of an informal proof to Euler's formula for connected planar graphs. Okay, questions? Of course, planar means we can draw them without crossings. Okay, so, and what that means is if we know 2 of the, if we know the numbers of vertices and the numbers of edges, we can determine the number of faces. But we can even do things, we can even draw more conclusions than that. So yeah. So the maximum number of edges in a simple graph, as mentioned, is the number of vertices choose 2, right? Because it's simply the number of subsets of my vertices of size 2. And that's equal to v times v minus 1 over 2. And this is big O of v squared. So, yeah. We want to find a different upper bound on the planar graph, on the number of edges in a planar graph. So this is not necessarily a planar graph, right? This is a complete graph, essentially. So on a complete graph, I have roughly the number of vertices squared for the number of edges. But on a planar graph, we claim that actually the number of vertices is at most linear in the number of edges, right? So that's a big sort of drop from a very, very dense graph to something that's a little less dense. Okay. So we're going to claim that the number of edges is at most 3v minus 6, and the number of faces is at most 2v minus 4, and we're going to get there through Euler's formula. Okay. All right, so what we're going to do is we're going to look at every face. We're going to number them 1 through f, in this case 1 through 6, and then we're going to make a new variable mi, which is the number of faces around, or sorry, the number of edges around that face. So we can see here, face number 1, m1 is equal to 3 because I have 3 edges bordering that face. I have 3 edges bordering this face, and we can see that this edge I've counted twice now, but that's okay. Each edge can border 2 different faces, or as in this case, it can border only 1 face. This borders face number 6 twice. Face number 3, this has 4 edges surrounding it, et cetera, et cetera. So each edge bounds either 2 faces or 1 face, as we discussed. So that means if I summed up all of these values, it's at most twice the number of edges, right? I can't have more than that. Each edge is counted at most twice. So in this case, this is counted once here and once here, and that's true for all edges. All right. On the other hand, as a lower bound on this sum, I could say, well, each face has at least 3 edges, right? I mean, there's a minimum size to my graph for this to be true. Right, if I just had this, right, if I only had 2 edges, then that's not true. So I have to have at least 3 edges total. But if I have at least 3 edges total, then every face is incident to at least 3 edges, because it has to be either a, it has to be a triangle. It can be a tree as well, and so you can have a bunch of adjacent faces that way. But yeah, or you can have bigger cycles. This is a face with 4, but it has to be at least 3. So now I have an upper bound and a lower bound on this sum. And now I can use that to just relate the number of faces to the number of edges, right? So I can just get rid of this altogether and say, well, 3 times the number of faces is at most 2 times the number of edges. And then I can say, well, I'll do a little bit of algebra, and I could say the number of faces is at most twice the edges over 3, right? I just divide both sides by 3. Okay, so now I have an inequality. These are what I'm trying to prove. This is what I already know, and this is what I already know. So I'm just going to plug this into Euler's formula and see if I can get to this guy. Okay, so I have this, I have Euler's formula. I plug that in for the faces, and then Euler's formula turns into an inequality. And, well, I can subtract 2/3 E from both sides. So I've got 1/3 E here that is less than or equal to V minus 2. And then I can multiply both sides by 3, and I get number of edges is the most 3 times the number of vertices minus 6. Okay, so from Euler's formula, we basically can get to here. And then to prove this other one, we're going to do something similar, but now we're going to substitute this in to Euler's formula. Oh yeah, sorry. We're going to plug this in, not into Euler's formula, but into this inequality. So I'm going to take this inequality, plug it into here. I believe I could. Yeah, that's fine. So then I get the number of faces is less than or equal to 2 times 3v minus 6 over 3. And we do a little bit of algebra. I get the number of faces most twice the number of vertices minus 4. Okay, so up till now, all algebra, but now we have Euler's formula, and we have a couple other formulas that we can use to prove things. All right. And yeah, the upper bound on the number of edges on a planar graph, should be sort of intuitive. If I start adding edges to this graph, well, at some point, I'm going to run out of places to put them. And then the next edge I add will induce a crossing, right? So I could add, there's, a maximal planar graph is a graph with the most number of edges you can have. But yeah, and then after that, I add more edges, I get crossings. Okay. All right. Questions so far? I told you, it's a lot of graph stuff. We're working our way to what the problem is we're going to solve, and then we're going to solve it using indicator random variables. And basically very similar to what we just did in the last example, right? It's not a lot more complicated than that. We just need all this background first. Okay, so we have a bunch of tools, and now we're going to look at complete graphs on n vertices, right? So a complete graph is called Kn, and what that means is that n is the number of vertices. So in this case, n is equal to 4, and the complete graph means I put every possible edge down, right? So here I have, between this vertex, I have an edge to every other vertex, and the same is true of every other vertex, right? So this guy is connected to the top and the right and the left. So this is the complete graph. This is the most number of edges I can have in a simple graph on n vertices. And what we notice is that, yeah, so I can count the number. I don't have to count the number of edges. I can compute it. It's V choose 2. Of course, as we talked about, it's all subsets of size 2 chosen from the set of vertices. So I can, for K4, we can see that it's planar because I have a drawing where there's no crossings. This is K5. This drawing has crossings, but we want to show that there's actually no drawing that exists of K5. K5 cannot be drawn without crossings. So that's the next goal here. So yeah, we claim that K5 is not planar, and well, we know that K5 has 5 vertices. We can compute the number of edges in K5. It's 5 choose 2, which is 10. And I mean, if you don't believe that, you can simply count them. It's not too difficult. Yeah, 10. And we've shown earlier that, well, using Euler's formula, that if it's a planar graph, the number of edges is at most 3 times the number of vertices minus 6. So we know the number of vertices is 5 in K5, and we know the number of edges is 10 in K5. So if it was planar, then this would be true. Because it's not true, then this is not planar. Right, so that's it. Right, so we could use this. This will not prove that a graph is planar, but you can use it to prove that a graph is not planar. simply just because of the way the implications go. All right, so because this is false, we've shown that K5 cannot possibly be drawn without crossings. Right. Questions? Okay. So then the next logical question is, well, we know some of them must cross, but now how many have to cross? So if our graph is not planar, then we want to draw it with the minimum number of crossings. Again, if it's not planar, if we minimize the crossings, we can minimize costs, right? It's not unusual to have chips where lines do cross, but every time they do, we have to put a new layer in. So we want to do that as few times as possible. So the minimum number of crossings in a graph is called the crossing number of that graph. Right, so I give you a combinatorial, just a list of, or a set of vertices and a set of edges, and you can determine, well, hypothetically, you can determine the least number of crossings that you can make in that graph. All right, so we will define for a graph G that CRG is the minimum number of crossings, and this is, or the crossing number of that graph. And if the graph is large, this is an NP complete problem, which means it's really hard to compute exactly, but we can prove certain things about it. But yeah, computing the exact number, depending on the size of your graph, would take a long time. There's approximation algorithms and things like that, but all right. So in this particular drawing of K5, we have 5 crossings, right? So one here, 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 and here. So yeah, can we draw K5 with fewer crossings? Well, let's try. Spoiler alert, yeah. So here I have 5 vertices, and I have edges between every pair of vertices, but I've just, moved them around a little bit and done a different drawing. And here we can see that we have only 1 crossing. All right, so that's, yeah, sorry, 1 second. Yeah, I believe that's a sign of spring. All right. Okay, so I've drawn K5 with a single crossing. And now the question is, well, is that the minimum number of crossings? Well, of course it is, because K5 is not planar, so I have to have at least 1 crossing in every drawing. And on the other hand, I found a drawing that has exactly 1 crossing. So that means the crossing number of K5 is 1. Right, so this is the best drawing that I can do. And by best, I mean the least number of crossings. Right, so to find the crossing number of a graph, I can find a lower bound. In this case, we can just use logic to determine that 1 is the lower bound. I mean, 1 is always a lower bound. And then if we find a drawing with that many crossings, then we found the crossing number. We can have trivial lower bounds, like 0 is another lower bound for the crossing number, but we know that that's not tight. So it's correct to say that 0 crossings is a lower bound of K5, the crossing number of K5, but it's not a tight lower bound. Okay. So now that we've seen K5, let's talk about K6. So to get K6, we're going to start with K5, the best drawing that we have of K5. And then we're going to introduce another vertex and try to minimize the number of crossings that occur. So I'm going to add a vertex here to my K5, right? I could have added it anywhere else. There's some good places and some bad places. This is one of the good ones. And then I'm going to connect it to every other vertex. Okay, so now I have the complete graph on 6 vertices. This is a drawing of it, not the only one, and we have 3 crossings. So we got 1 here, and 1 here. All right, so we know that the crossing number is at most 3, since we can draw it with 3. The question is, can we draw it with fewer than 3? Right, so the crossing number is at most 6, but if we can draw it, say, with 2, then the crossing number would be 2. Okay, so we want to find a lower bound of our crossing number of K6. So what we want to do is, we want to find a function, some function of the number of vertices and the number of edges, such that we can determine a lower bound on the crossing number. And we're going to use some of these formulas that we've derived. So so we're going to take a drawing of G, and we're going to assume that we've drawn it the best way possible. So we're assuming that G has been drawn with the crossing number of crossings. So you can imagine perhaps this is optimal. In this case, CR of G would be 3, but we're talking about any graph. And we're assuming that we've drawn it perfectly. Now, if I wanted to make that into a planar graph, what I'm going to do is take every crossing and I'm going to make it into a vertex. Okay, and then we're going to look at what that does. Now we have a relationship between the number of vertices, edges, and faces in a planar graph. If I put a vertex at every crossing, I've made my graph planar. So let's look at the impact it has on the numbers with respect to the number of crossings. Okay, so every crossing splits an edge into 2 edges. Splits 2 edges into 2 edges. So I add a vertex at the crossing. So for every crossing, I'm going to add a vertex to my graph, right? And for every crossing, I'm going to add 2 edges, right? So originally in this crossing, I had 2 edges involved, and now I have 1, 2, 3, 4 edges involved, right? So every time I put a vertex at a crossing, well, I get 1 more vertex. So the number of crossings, V plus the number of crossings, is my new number of vertices. And my edges, every crossing introduces 2 new edges. So I have my old number of edges plus 2 times the number of crossings. And then I have some formulas that can relate these numbers. Right, so I can, if my graph is planar, which it is, then the number of edges is at most 3 times the number of vertices minus 6. Well, my new planar graph, I have my edges plus twice the crossing number is my new edges, and my vertices plus the crossing number is my new vertices. But this equation still holds true. And then I can solve for the crossing number. Okay, so the crossing number of G is at most, or at least, the number of edges minus 3 times the number of vertices plus 6. Okay, just through a little bit of algebra and introducing these new vertices. Okay, so in a complete graph, well, in K6 in particular, but any complete graph, we have V choose 2 as the number of edges. So for K6, the number of edges is 6 choose 2. And if I plug that into my formula, then I get 6 choose 2 minus 3 times the number of vertices, which is 3 times 6, or 18, plus 6. All right, so that means, well, 15 minus 18 plus 6 is equal to 3. So that means the crossing number of K6 has to be at least 3. It can't be any lower than that. And even though we did not look at every possible drawing, we proved it using Euler's formula and, and a couple little tricks, I guess. Okay, questions? I promise there's probability. So any drawing of K6 must have at least 3 crossings, and we've actually drawn K6 with exactly 3 crossings, which means that we found the crossing number. right? So the crossing number of K6 is 3. That is the best possible drawing of K6 is with 3 crossings. Does that make sense? Okay. So we've looked at some graphs. We've introduced complete graphs. We've looked at Euler's formula. We've introduced the crossing number. We found the crossing number of, well, K4, K5, and K6. Now we want to prove something about, generally about the crossing number of complete graphs. So if we look at Kn, I can say, well, for any, if I have n vertices in a complete graph, then the number of edges is n choose 2. So I can use my lower bound of the crossing number and plug in my edges. I can substitute n choose 2 in for my edges. So my complete graph Kn must have at least this many crossings. And that's, not saying much, except this n choose 2 is, of course, big O of n squared, right? It behaves as there's a few constants and lower order terms in there, but it's big O of n squared. And these are lower order terms, which means this entire thing is, well, big O is the wrong way to put it, but because this is a lower bound, this is big omega of n squared, right? So the crossing number of the complete graph on n vertices grows at least as fast as n squared in n. Okay, so we found a general lower bound for the crossing number of the complete graph. And now we want to try and find an upper bound so that we can say, well, in general, the complete graph has exactly some function of n many crossings. All right, so we want to find an upper bound. So the question is, well, is the upper bound on the crossing number n squared? So is any Kn, would I expect to have some order of n squared crossings? Well, we could find a simple bound, upper bound on the crossing number. So if I look at every pair of edges in my complete graph and say, well, every edge crosses every other edge, then every pair of edges forms a crossing. So that would be, if I choose all pairs of edges from the set of edges, then there are E choose 2 of those. So at most, and that's the most number, an edge can't cross another edge twice, right? So each pair of edges can cross at most once. So I can only have at most E choose 2 crossings. Well, I know that on the complete graph, E is n choose 2. So n choose 2 is big O of n to the 4. Okay, so yeah, this is basically, I get one n squared here, and then I get another n squared when I apply it there. Okay, big O of n to the 4. So I have a lower bound of the crossing number of the complete graph of n squared, and I have an upper bound of n to the 4, and I'm trying to find what's the tight bound, right? So that means that I have a matching upper and lower bound, essentially, which I don't right now. So the actual crossing number can be anywhere from n squared through n to the 4. Okay, so one of these is correct, or maybe n cubed is correct, or n cubed log n. So which of these, possible functions in that range is correct? It turns out that the actual lower bound is omega of n to the 4, which is what we're going to prove using probability. Finally, right? So we found a sort of a loose lower bound earlier using, Euler's theorem and some of the things that we knew, but now we're going to find a tighter lower bound. Okay, questions? All right. So that is all the background. From here on out, it gets kind of, well, not easy per se, but stuff that you are more familiar with. So I'm going to take an arbitrary graph G, and I'm going to take a probability P that is between 0 and 1, and I'm going to make what's called a random graph. And all I'm going to do is I'm going to look at each vertex in G, and then I'm going to include it in my random graph with probability P. So similar to how we, partitioned our vertices before, but now one partition is just I throw it away. So I either keep the vertex or I throw it away. And if I throw that vertex away, I throw away all the incident edges. Okay, so any arbitrary graph, and then I'm going to choose a random graph, and an edge AB from the original graph will appear in the random graph if both A and B are in the random graph. All right, so my original graph looks like this. My random graph looks like this. If this is A, B, and C, then only A and B is kept. C is gone, and all the incident edges are also gone. Okay. So now we will define some random variables. So V of P is the number of vertices in my random graph, which I don't know. It's going to be randomly determined. E of P is the number of edges in my random graph. And we'll say that X of P is the crossing number of my random graph. So I'm going to take my random graph. I'm going to do the best drawing possible and find the number of crossings and find the crossing number. Right? So X of P is the crossing number of my random graph. Okay. So we're going to apply this lower bound to the random graph. Right, so the crossing number of my random graph is at least the number of edges minus 3 times the number of vertices plus 6. So then I have this, I can define this random variable in terms of these random variables, right? So the number of edges is E of P, the number of vertices is V of P. So yeah, we can do a little bit of algebra and move these 3 terms, put them together. So the crossing number minus the number of edges plus 3 times the number of vertices is at least 6. I'm really looking at large numbers of n here, so I don't really care about this 6. So I'm just going to drop it. I'm going to say, well, if it's at least 6, then it's also at least 0, right? This is true. And then I can say, well, I can define this as a random variable and then just take the expected value. And then I can use linearity of expectation to say, well, that's equal to this. Okay, so I have an expression with the expected number of crossings minus the expected number of edges plus 3 times the expected number of vertices is at least 0. Okay. Question so far? All right. Okay, so let's determine these expected values, and that's rather simple. I mean, we only have one operation. We have vertices, and we, keep it with probability P. Otherwise, we throw it away. So my expected number of vertices, and here I've skipped a step, right? I could look at every vertex individually, say V1, V2, or I can define indicator random variables. V1 is equal to 1 if vertex 1 stays and 0 otherwise. Since these are indicator random variables, the expected value of V1 is simply equal to the probability that I keep it. All right, so then I can express, well, the expected number of vertices is simply I sum up all of the indicator random variables from all the vertices. All right, so I've skipped a step here with my indicator random variables, but hopefully that's not, yeah, we finally get to probability and I skip over the probability parts. That's pretty funny. All right. So if I sum up all V of my vertices, each having or the expected value of each of these indicator random variables. They're all V of them, and each has a probability P, then I get V times P. All right. I can do the same thing for the edges. Yeah, and I'm implicitly using indicator random variables here. So an edge UV is in my random graph if both U and V were selected, right? If only one was selected, that edge is thrown away. But if I select both, then then that edge stays. The probability that I've selected both U and V is equal to, well, it's probability P that I select U and probability P that I select V. So that is P squared. Right, so the number of edges in my random graph, well, if I set up some indicator random variables for each edge, well, the expected value of that indicator random variable would be P squared, and there are E of them, so I would simply sum them up. So the expected number of edges in my random graph is P squared times the number of edges in my original graph. Okay. Finally, I can find the expected number of crossings. So a crossing occurs in my random graph if I find a crossing in my original graph and I keep all 4 vertices, right? So this A, B, C, D is a crossing in my original graph G. And if I keep all 4 vertices, then that crossing will stay. Yeah, sort of. Sorry, I may have misspoken there. No, that's true. All right. It's not quite accurate because I can always redraw the graph, but it gives a bound. Okay, so then the probability that I keep all 4 vertices is, of course, P to the 4th. It's probability P that I keep A, probability P that I keep B, P that I keep C, and P that I keep D. So keeping all 4 is P times P times P times P, which is P to the 4th times the number of crossings in my original graph. Okay. Yeah. All right. Oh, that does hold. I was just thinking of because yeah, you can redraw, but this is the best drawing we have. So yeah, this is what I'm telling you is almost true, just close enough. Okay, so now I can express this as I can plug in my expected values. So this is P to the 4th times the crossing number of G minus P squared times E plus 3 times P times V. Okay, and well, the nice thing is I've now introduced the crossing number of my original graph into this formula. So now I can rearrange it to solve for the crossing number. Right, so if I do some fancy algebra, I have that the crossing number of my graph G is at least P squared times E minus 3 times P times V over P to the 4th. And this is true no matter what value I choose for P. Right, so I can choose P equal to 1 or, well, not 0, but, and this value always holds. So what I want to do is I want to find the value of P that makes this expression the highest, and that's my new lower bound on the crossing number of a graph. Right, so since I can choose any value P, if we did the work, we can figure out that, yes, well, actually, I don't even think this is optimal. I think you can do slightly better, but this gives us asymptotically optimal. So if we take the probability P is equal to 4 times the number of vertices over the number of edges, and we can only do this if we have at least 4 times the number of edges as vertices, right? Because otherwise this is going to be greater than 1. So if we plug that in, then we get, and we do a little bit of massaging, which we're going to skip. We get the crossing number of G is at least 1 over 64 times E cubed over V squared. Right, so the P's will be gone and replaced with V's and E's. Okay, so we have a new lower bound of our crossing number. This may mean nothing at this point, but questions? All right, so we have a new lower bound. And well, if I look at my complete graph now, so this is true for any graph. If I look at my complete graph, well, I can say something about the number of edges. I could say that the number of edges is n choose 2 cubed, and n choose 2 is about n squared. So n squared cubed is n to the power 6. And then, so then I cancel out n squared. I get n to the 4th. And the crossing number of my complete graph on n vertices has to be at least n to the 4th, some function of n to the 4th. Okay, and that is, so that's basically the crossing lemma. Questions? Okay, so this is sort of I mean, it's considered a higher level proof, but you guys have the tools essentially to do that. I mean, there's a bit of nasty arithmetic there, but it's not, it's still high school level arithmetic. So for large values of n, the crossing number of the complete graph is has a tight bound of n to the 4th. All right. That's that. Okay, so we got about 10 minutes left. So we'll just go back to something. This is not quite, we're just going to do the first part of this question, the part on X. The part on Y is really nasty. The part on X is kind of nasty, but I also know that there's at least one, if you look at the old exams, this is actually one of the questions, right? The expected value of X. This is from the one of the old exams, so I'm going to show you here in case maybe I don't show it to you at another time. So yeah, the problem is as follows. I'm going to have, let n at least 2 be an integer. So I have n cider bottles, C1 through Cn, and I have 2 beer bottles, B1 and B2. I'm going to take a uniformly random permutation of them. So I'm just going to line them up on the wall in some order. And then I'm going to define, well, X and Y, but we're really going to focus on X. X is the position of the first cider bottle. Okay, so in this example here, I have 5 cider bottles and 2 beer bottles, and my first cider bottle is at location 2. Then X is equal to 2, and Y is equal to 5, but we're ignoring that. So I want the position starting from the left of the first cider bottle. So that's my random variable X, and I want to determine the expected value of X. And it's a little painful, but it's not too bad. It's I would consider it a harder, one of the harder exam questions. Okay, so the expected value of X, well, we just go back to our definition of expected value. Well, let's take a look. What's the range of X? So what values can X have? Well, the leftmost beer bottle can be, the leftmost cider bottle can be 1. I could have, I could start with C3 and then B2 and then C4, etc. So my first bottle can be cider. I can have the second bottle cider, right? As in this example. So I can have X equal to 2. I can have the third bottle being cider. So I have two beer bottles, B1, B2, and I can have C3 in the third spot. But then I run out of beer bottles, right? So in the worst case, in terms of, how far to the right can my first cider bottle be? Well, I only have two beer bottles that can go in locations 1 and 2. So I can only be as far as location 3 away from the beginning. Okay, so the position of the first cider bottle, my random variable X has values 1, 2, or 3. Okay, so this means, well, seems like a good candidate for this version of expected value, which is I iterate over the range, k equals 1 to 3, k times the probability that X is equal to k. All right, so then it's just 3 terms that we have to determine, and then we can sum them up. Okay, so is everybody clear on the problem? Is there any questions? Okay. All right, so mainly what we want is the probability. I mean, this is simple enough, but we need the probability that X is equal to 1, probability that X is equal to 2, and the probability that X is equal to 3. So what do we know? Well, X equal to 1 is just an event where my cider bottle comes first. These are uniformly random permutations of n plus 2 bottles, right? N cider and 2 beer bottles. So I'm going to, since it's uniformly random, I'm going to just use counting arguments, the size of this event over the size of the sample space, which is n plus 2 factorial, right? All possible permutations, there's n plus 2 factorial of them. So now I just really want to count the number of arrangements where my cider bottle is the the cider bottle is the leftmost bottle. Okay, so how many? I'll just use the product rule. So first thing I'm going to do is, I know there's a cider bottle in the first location. So which one? Well, I have n to choose from. So I have n choices for that first cider bottle. After that, I don't care. I can put any arrangement I want. I have n plus 1 bottles left and n plus 1 locations. So that is n plus 1 factorial. Okay. So then I can cancel out n plus 1 factorial and n plus 2 factorial and get n over n plus 2. Okay, does it make sense? Questions? Okay, so I have the probability that X is equal to 1. Let's get the probability that X is equal to 2. Same procedure. I have my sample space is all permutations, but now I know the first location has to be a beer bottle, and then the second location is a cider bottle. So same thing, choose one beer bottle to go first. I have 2 available, so I have 2 choices for that. Location 2 is a cider bottle. I have n cider bottles that I have not placed, so I have n choices for that. And now I filled the first 2 locations. I have n locations left and n bottles. I don't care what order they're in. So this is n factorial. Again, we can simplify a little bit. This is 2n over n plus 2, n plus 1. Right? This n factorial cancels out with all but the last 2 terms of n plus 2 factorial. Okay. So that's probability that X is equal to 2. Questions on that? Okay. Probability that X is equal to 3. Again, it's a similar procedure. N plus 2 factorial. So now my first 2 locations are beer. I know that, and there's basically only 2 ways to put it. I can have B1, B2, or B2, B1. So there's 2 ways to put beer in the first 2 locations. So I have 2 choices for that. And then everything else is cider. So whatever order I put them in, it doesn't matter. So I can take my n cider bottles and my n locations and take all permutations. Okay, so then I get 2 times n plus 2, n plus 1. Okay, so I have, yeah. So now I have all my probabilities. I just need to sum them up with my multiplied times the value of x. So in the first case, hopefully I'm not too far off here, but expected value of x is equal to the 1 times the probability that x is equal to 1 plus 2 times the probability that x is equal to 2 plus 3 times the probability that x is equal to 3. So now I simply, well, 1 times the probability x equal to 1 is n. Well, I'm going to put everything with a common denominator. If you see it on the quiz or on the final, it'll have a common denominator. So instead of n over n plus 2, I'm going to multiply the top and bottom times n plus 1. All right, so this is going to be n plus 1, n plus 2 times n plus 1. All right, so these guys both have a common denominator. I'm just giving this guy the same common denominator. Okay, so then I have n times n plus 1 plus 2n times 2. So that's plus 4n plus 3 times the probability x equal to 3. So 3 times 2, which is 6. Okay, so I have my expected value here, and then I can, n squared plus n plus 4n plus 6 over n plus 2, n plus 1, and yeah, 4n plus n. Yeah, I did that right. Okay, it's 5n. So yeah, if you see one of the old exam questions, it's, I'm pretty sure exactly this, and it's multiple choice, and all of the answers look similar to that. So that's how you would do it. And it's probably one of the, again, one of the harder ones that would appear on the final. But there's precious few easy exercises in terms of expected value and indicator random variables. So I thought this would be appropriate. So yeah, any questions? Yeah. Yeah, like you wouldn't see, it wouldn't be every question, but there might be one question where you're expected to do this much work. Yeah. Is that what you're asking? I'm sorry.
Quadratic and numerator x squared plus 5x plus 6. You can factor that and then put the solution.
Oh. Well, I mean, if we gave you that, then you could, I mean, you could relate that, those two polynomials, right? If I did factor it, I mean, you can either try and factor this, or if I gave you something, whatever it happened to be, what is it? Is there anything that does that? I don't know. But if there was, you could quickly determine if they were the same, right? Yeah. So yeah, I suppose that is possible. I mean, I'm unlikely to give you, I don't like stuff that's hard to understand what I'm asking, right? As long as it's clear what I'm asking, then I figure it's fair game. But when I try to obfuscate the answers, I don't really like doing that either, even though I sometimes do it. Yeah. All right. Section A have 2 lectures next week. No, I think it's just 1, right? What's that? Wednesday is Friday's schedule. Yeah. No, I think it's you guys have 1 class. We'll take up an old exam, and then section B has 1 class. We'll take up an old exam, a different one, so that if you guys want to watch the video, you can. And then, yeah, that's it for the week. So yeah, any other questions? Okay, so I don't know, have a good Easter weekend and I'll see you guys next week. So, I mean, I'm sorry for the state of assignment 4 being sort of in doubt, but please continue to work on it for now until you hear official word. Yeah. Yep, 25 questions ago. Yeah, 2 hours, 25 questions. Sorry? Yeah. Roughly, yeah. Yeah. It might be off by, I mean, I might focus a little more on expected value and indicator random variable, but yeah.
Hi, how are you?
Good. How are you?
I'm good, thank you.
Yeah.
I wanted to ask you about assignment 4. I'm not sure if you talked